Hi guys, welcome to Electronics 1, a course for college and university students. This time we are going to look at intrinsic and extrinsic semiconductors. As usual, your presenter is Moshen Marufu, and for any comments and suggestions, you can get in touch with me on moshenmarufu68@gmail.com or +26371753586. Let's enjoy this one. Just two objectives in this presentation. One, define intrinsic and extrinsic semiconductors. These are the basic two types of semiconductors. Then objective number 2, describe P-type and N-type semiconductors and their characteristics. P-type and N-type are extrinsic type of semiconductors. What basically is an intrinsic semiconductor? An intrinsic semiconductor is a semiconductor in its purest form. In other words, one part in every 100 million parts. That means one impurity to every 100 million parts of the pure semiconductor. That is an intrinsic semiconductor. Please take note that silicon has got 4 electrons in its valence shell, and to share or for it to be stable, it needs 4 electrons. And how does it achieve that? It shares with 4 nearby silicon or germanium atoms. Then its valence shell will now contain 8 electrons, and that atom becomes stable. So it means that if we have many silicon atoms having their valence shell full, we form what we call a crystal structure. So that basically is an intrinsic semiconductor. To look at bonding. From your high school, you know what bonding means. We've got covalent bonding and electrovalent bonding. And we are saying when atoms bond together to form molecules, each atom attempts to acquire during the process 8 electrons in the valence shell so that it becomes stable. When the valence shell is containing 8 electrons, it means it's now full. It cannot exceed that. Hence, that material is now stable. And if the outermost shell of an atom has 8 electrons and it is said to be full, it cannot accept more. An intrinsic semiconductor has only 4 electrons in its outermost shell, so it needs 4 for it to be stable. How does it gain those 4 electrons? By sharing with 4 atoms, each donating 1 to each of the 4 atoms. As a result, the atom at the center will have 8 electrons in its valence shell. Then it becomes stable. So what that means is a silicon or germanium a crystal is pure. Why? Because it only contains either germanium or silicon atoms only, and they will be sharing a silicon. That slide is simply an explanation of the previous diagram. Guys, go through it on your own and see if it makes sense. Large carriers generation in an intrinsic semiconductors. We are saying when an electron is energized, it escapes from the valence band into the conduction band. In other words, it breaks the covalent bond. So this electron has been energized, and after being energized, it has left this bond and it's now free. In other words, it's now in the conduction band. As you can see from the energy band diagram, the electron was in the valence band and it is now escaped the valence band after acquiring enough energy gap to land in the conduction band. So it has left a hole. So electrons and holes are charge carriers in an intrinsic semiconductor. So we are saying electron hole are created, or electrons and holes are generated in pairs, which means that the concentration of free electrons and holes will always be equal. But that is only in an intrinsic semiconductor. In a pure semiconductor, and that which has caused this electron to escape from the covalent bond or to detach itself from the covalent bond to become free or to escape from the valence band to the conduction band, we call that thermal generation or thermal agitation, which simply means heat increase. I've said an electron warp pair is generated when an electron leaves a covalent bond, or when an electron leaves the valence band and proceeds to the conduction band. And since it is negatively charged, it means that the site of a hole will be left with a net positive charge. Thus, we say a positive charge is associated with a hole, or we can say a hole is positively charged. That is the concept. The hole in itself, we also call it a charge carrier, since it is positively charged. So it also results in flow of current. So we say it too carries charge from one point to another, but it results from the movement of an electron. If an electron does not move from the valence band to the conduction band, then there is no hole that is generated. A random movement of charge carriers. What are we saying? We are saying charge carriers in an intrinsic semiconductor, which are holes and electrons, they move randomly, they move haphazardly. So we are saying both types of charge carriers move randomly or haphazardly in a crystal, and this is how it happens. A free electron, after being excited, moves in a crystal due to thermal energy, or from an increase in temperature, or from heat. Wherever it goes, there's a possibility of encountering a hole. So this gives rise to a zigzag or a random motion, which is what happens to gas molecules in a gas container. And we are saying, although the movement of holes actually consists of the movement of electrons, we are saying hole movement is different from the movement of free electrons, because why? Electrons move, or they escape from the valence band to the conduction band, while holes move because of the movement of electrons from the valence band. So what initiates the movement of a hole is an electron. If an electron does not escape, therefore no hole is created. What I am simply saying, if for example, when you are in a queue, if the person in front of you does not move, then you don't move. So you move when the person in front of you has created a hole or some space for you to occupy. That's exactly what happens when electrons move in an intrinsic conductor. That slide showing haphazard or random movement of charge carriers. And charge carriers, we said, are holes and electrons. So we've got A, B, C, D, E, and F, and we are starting from A. An electron is escaped from its bond, and this is the bond, and it's now there. So it means a hole has been created. As we have said, electron hole pairs are created simultaneously, right? Because we now have a hole, it means that this hole can be occupied by an electron anytime. And if we go to diagram B, an electron from point B is now occupied, an electron at point B has now occupied the hole at point A. So we are saying this is random movement. It's a haphazard movement of an electron. And if we go to diagram C, we are saying A is now being occupied by an electron that is moved from B. So the hole is now moved from A to B. And if we go to diagram D rather, we are seeing that an electron from C has now occupied the hole that was created at B. In other words, we are now going to have an electron moving, the hole moving from B to C as shown on E. So in other words, a hole is moved from this point to this point and it's now there. This is a random movement. So as shown on F, we can now finally say a hole is moved from this point to this point and to this point now, as shown on F. In other words, it is the electrons that started the movement of a hole. So we now have electrons moving from this to this and to this, and a hole moving from there to there. So this is random. This is an illustration of haphazard movement of electrons and holes. More on haphazard movement. From the slide, you can see that the electron has moved from C to A, then to B, then from B it has gone to A. This is an illustration of random movement. Then it has acquired enough energy that is greater than the energy gap. Then so this is the valence band. So it has now acquired more energy than Eg, which is the energy gap. So it has jumped from the valence band to the conduction band. Right, so the two most important bands are the valence band and the conduction band. The other bands for the inner shells are not very important. So this is what we call the random or the zigzag or haphazard movement. For example, the electron was moving in the valence band from hole to hole. So it is hole current we'll be talking about as long as the electron is moving in the valence band. Due to thermal agitation, it has now acquired enough energy and it has left a hole, meaning that the electron has escaped from the valence band to the conduction band. And in the conduction band, you can as well see the haphazard movement. So this is just a demonstration of the fact that the electron, due to thermal agitation and also holes, move in a haphazard manner or in a zigzag manner or in a jumpy movement. I have gone through the explanation of the movement of a hole from A to C while an electron moved from C to A before eventually crossing the energy gap into the conduction band. A recombination of electrons and holes. We are still on intrinsic semiconductors. We haven't done justice yet to that. And we are saying in an intrinsic semiconductor, electrons and holes are generated continuously due to thermal agitation or due to heat. And we said since electrons and holes move in the crystal in a randomly or haphazard manner, there is a chance of an electron meeting a hole because of the random movement. And when that happens, both the electron and hole disappear because why? The electron is going to occupy the hole. So this is going to establish a covalent bond again. And we are saying at any temperature, the rate of this recombination is equal to rate of generation. And we are saying, however, an electron travels some distances before it meets a hole. And we are saying the average time that it takes an electron to meet a free hole is called the lifetime. Conduction in any intrinsic conductor. This is our intrinsic conductor, and it has got, we know that we have got holes and electrons. So what is going to happen is we've got a voltage source, a battery with positive and negative. And we know that we have got some electrons in the intrinsic material. And we know that unlike charges attract, so the positive terminal of the voltage source is going to attract the electrons, and the electrons are indicated by this dot. The black dots, they are representing electrons. So the electrons, by the direction of the arrow, they are moving towards the negative terminal of the battery because unlike charges attract, and the holes, these white dots are the holes, and they are going to move towards the negative of the battery. Because in an intrinsic conductor, the number of holes is equal to the number of electrons, and they are produced by thermal agitation or thermal generation. So we have got what we said electron hole pairs. So this is what happens, and we are saying the electrons, due to the current flow due to the movement of electrons is represented by In, where this is negative, and the electric current due to holes is represented by Ip. We know I is the symbol for current, and this P stands for positive. Please take note that we have got what we call conventional flow of electric current. It says that current moves from the positive terminal of the battery to the negative terminal of the battery. Hence, we have got in this direction the sum of the two currents, and we call this net current flow. That slide is an explanation of conduction in an intrinsic semiconductor when a voltage is applied. Go through it and see if it makes sense. I've gone through the explanation. The current due to the applied voltage is called drift current, as we have seen in the previous slide, and the current due to an equal distribution of charge carriers is called diffusion current. And we know from our high school what diffusion is. Diffusion tries to attain equilibrium. So diffusion current is caused by gradient of carrier concentration, which is the difference in concentration near the boundary of the PN junction. We'll be looking at the PN junction in a video ahead. And we also know that diffusion current is also due to the motion of both holes and electrons. So we are simply talking of diffusion current in this slide, apart from the drift current. The effect of temperature on conductivity of any intrinsic semiconductors. We've discussed that a semiconductor behaves as a perfect insulator at absolute zero temperature, that is at minus 273 degrees Celsius. And at room temperature, and due to thermal agitation, we are going to have some electrons gaining energy and escaping from the valence band into the conduction band. This is going to avail free electrons that will lead to an increase in conductivity, because we are going to have, for example, a charge carrier concentration of either free electrons or holes of 2.5 times 10 to the power 19 per cubic meter. But even at this room temperature, we still have got a very low conductivity of the intrinsic semiconductor. So how can we increase it? We simply increase the temperature. An increase in temperature results in electrons in the valence shell acquiring energy and escaping from the valence band or from their atoms into the conduction band, where there will be free electrons and aid in the conduction of that particular intrinsic semiconductor. So as we increase the temperature, we also increase the amount of charge carriers. That is, we reduce the resistivity of that intrinsic semiconductor. Hence, semiconductors have a negative temperature coefficient. Extrinsic semiconductors. All along we've been looking at intrinsic semiconductors, which are pure semiconductors. Extrinsic semiconductors are semiconductors to which some impurities, which are group 3 or group 4 atoms, have been added in controlled quantities to improve conduction. And we know that practically almost all electronics devices are made from extrinsic semiconductors, or materials to which some impurities have been added to improve conduction. And this process of deliberately adding some impurities in a controlled manner to improve conduction of the semiconductor is called doping. And this is only done after attaining a high degree of impurity. And we said a pure semiconductor has got a proportion of 1 impurity to 100 million parts of the semiconductor. So we are saying a doped semiconductor is an extrinsic semiconductor, and we have got two types: N type, N standing for negative, and P type, P standing for positive. N type semiconductors, that N stands for negative, which means the semiconductor will be having a charge of minus or negative. The impurity added to an intrinsic semiconductor to improve its conduction is called a dopant. And we have got two types of dopants, trivalent as well as pentavalent. Pentavalent atoms have 5 electrons in their valence shell, and phosphorus is a good example. Trivalent atoms have 3 electrons in their valence shell, and boron is also a good example. And we are saying when we add a germanium or a silicon atom to when we add a pentavalent or a trivalent atom to an intrinsic semiconductor, a crystal, it is going to displace the silicon or germanium atoms, and it is going to share electrons with 4 nearby silicon or germanium atoms. Because a pentavalent has got 5 electrons, it means 1 electron will not be attached to any atom. Hence, it will be referred to as free. And the more pentavalents we add, the more free electrons we have. Hence, the designation any type. Let's proceed to the next slide to see what happens. Formation of an N-type semiconductor. We have doped with a pentavalent atom, and the pentavalent atom is now at the center. It has displaced 1 silicon or germanium atom. So it has said it's 4 electrons in the valence shell with 4 nearby atoms. 1, 2, 3, 4. So this electron belongs to the pentavalent atom, and this belongs to the silicon or germanium atom. The same applies to this and this and this. This has got 5 electrons in the valence shell. So this is the 5th electron that has not been bonded to any germanium or silicon atoms. The more pentavalent atoms we add, the more free electrons we have. The +5 is at the nucleus of the pentavalent of the pentavalent atom. Why? Because we are not considering the 5 valence electrons which are now attached to nearby atoms, and this one has escaped. It's no longer attached to this. Hence, the nucleus has got a +5 designation. So we are saying pentavalent atoms have got 5 electrons in their valence shell. This we have seen 1, 2, 3, 4, 5. And we are saying the 5th electron, which is this one, becomes a free electron since it is not attached to any atom. So this is how any type semiconductor is formed. Any stands for negative, which comes from the availability of excess free electrons. That slide is simply explaining what I've been doing for the previous slide. I went through it. So you can go through it on your own and see if it agrees with my explanation. But please take note, the dopant or the pentavalent atom is called a donor since it donates an excess electron, and we are saying the excess electron becomes free. So we are saying all electrons which have been donated by impurity atoms can take part in the conduction of electricity. The number of free electrons becomes far greater than the number of electrons if we increase the number of dopants. Thus, we say that an N-type semiconductor has got electrons as majority charge carriers and holes as minority charge carriers. And the minority charge carriers are produced due to thermal agitation. Please take note, we don't dope with a pentavalent atom to produce minority charge carriers. A representation of N-type semiconductor. The letter N stands for negative because the electrons are the major charge carriers and electrons are negatively charged. It does not mean that a sample of N-type semiconductor is negatively charged. Why? Because we know that it remains electrically neutral because the number of electrons is equal to number of protons in each designated individual atom. We said free electrons and holes are generated in pairs due to thermal agitation. The negative charge of free electrons is is exactly balanced by the positive charge of the holes. So we are saying in any type semiconductor, there are additional free electrons created because of doping with pentavalent atoms. And take note of the last point. We've got some immobile ions. They also balance the negative charge of the electrons. Conduction in any type semiconductor material. What are we saying? We are now applying a voltage to any type, and we know our majority charge carriers are electrons, but due to thermal agitation, we also have minority charge carriers as holes. These are holes. How many do we have? 1, 2, 3. So they are less than the number of majority charge carriers, which are electrons, which are the solid dots. So when we apply a voltage source, unlike charges attract electrons, which are these are going to be attracted towards the positive terminal, while holes, which are minority charge carriers, are going to be attracted towards the negative terminal of the applied voltage. But we know that conventional current flows from positive to negative. Hence, we are saying in any type semiconductor, we now have free electrons large in number because of doping. P-type semiconductor. P stands for positive, and this is formed when we dope a semiconductor crystal with a trivalent atom or trivalent impurity. Trivalent atom has got 3 electrons in the valence shell, which means if we add it to a semiconductor crystal, it will form covalent bonds with only 3 atoms, and it is finished, which means that we are going to have an incomplete bond with the 4th semiconductor. Why? Because it only has got 3 and it is finished, which means that that hole has got a potential of attracting an electron from nearby or from zigzag moving electrons. Hence, because it can attract electron, it means that its charge is positive. Hence, we are saying we have created a p-type semiconductor because holes are positively charged and can attract electrons. We are now going to have a look at hole formation in a p-type semiconductor. We are doing an explanation of hole formation, and I think I can add 1 or 2 things to that. We have said a vacancy is created on an incomplete bond and we call it a hole, and we are saying if we add more trivalent, we are going to have more holes, and we can only have electrons due to thermal agitation. So holes are majority charge carriers in p-type and electrons are minority charge carriers. Because the dopant is a trivalent with 3 electrons, we call it an acceptor type because it has the potential to accept an electron. Conduction in p-type semiconductor. We have applied a voltage to the p-type semiconductor, and we know that majority charge carriers are holes. These are the white dots, and if you count them, you will see that they outnumber the black dots, which are electrons. Unlike charges attract, the positive terminal of the battery is going to attract electrons. As you can see, electrons are moving in the direction of the positive terminal of the battery, while holes are moving in the direction of the negative terminal of the battery because they are attracting. As I said, in the n-type material, we are going to have holes moving in this direction being occupied by holes being repelled by the positive terminal of the battery, and also electrons moving in this direction. They are going to escape from their atoms and they are going to go through the battery to the negative terminal and repelled in this direction. So in other words, we are saying in the semiconductor, conduction is due to holes and electrons, while in the wire, conduction is due to electrons. But conventionally, current flow through the wire is through holes and electrons. As you can see, they are moving in this direction, which was the old way of describing the flow of current in a conductor. But now we know that current moves from negative to positive. This is the end of our second video presentation on intrinsic and extrinsic semiconductors. Next time when we meet, we'll be talking about the most basic electronic device, which is a PN junction diode. Until then, enjoy yourself, guys, and please, social distancing.